Okay, so welcome back to lecture 9. And this week we're going to move on from the study of kinematics to what's called the study of dynamics. Okay, so what does these word means? I think it's really just a terminology to confuse people. Really, to be honest, really it's part of the same story, but just for teaching purpose, a lot of books and courses sort of separate these out just to let you know. To me, it's semantics, but just to let you know what the word means. Usually, when people say kinematics, both kinematics and dynamics, it's really this theory of motion and how and why things move. How do they move? Can I make predictions about motions, etc. Right? But usually people make this distinction where kinematics is really the study of how these kinematics variables, right? The position, the velocity, acceleration, and time, how they relate to each other with those kinematics equations, or we can use the Suvat equations, right? Or the formal kinematics equations. That's how all these guys are related to each other. So that's the study of kinematics without regard of the forces. Okay, so you almost ignore the forces and just look at how these variables are related together. And we have four kinematics equations, or the Suvat equations, and you see that they're related to each other. Actually, there are 5 variables, right? So there's actually 5 kinematics equations. I don't know if you've ever thought about it since you first learned it. There were 4 Suvat equations, and each one is missing a variable, right? I would challenge you to think about. Well, if there's 5 variables, there should be 5 equations, one for each missing variable, right? So we're missing one equation. Have you noticed that? And what is it? Right. See if you can pause the video right now and think about which one's missing, and see if you have memorized them and remember the equations well. Okay, I'm going to review the answer now. You're missing an equation that has no u, right? There's an equation with no s, no v, no a, no t, but there's no equation that has no u. In fact, there is an equation that has no u. However, it's much rarer you need to use it precisely because as I always try to bring you in the main picture of what are we doing in physics, is trying to predict the future. Usually we're trying to have the present and predict the future, right? So sometimes we don't know v, so you want an equation with no v just in case we don't have it and we still need to make predictions about time, about acceleration, etc. But usually we know the initial state, right? Of course, sometimes, like I gave some examples, you need to find it backwards. If you need to, just go and pick remember you start off with two fundamental kinematics equation, and then you just derive the other 2 by eliminating the variables that you don't want to appear in there. So you just go back to your first 2 and then eliminate u, and you get the 5th one, right? But it's so rarely used that it's not worth committing to our memory, right? We all have limited memory space in our heads. Let's commit them to something useful, right? So that's kinematics. And dynamics is really the study of motion by looking at forces. So this is looking at motion without forces. This is looking at how forces interact, right? But to me, really, it's all part of the same story. Yeah, so this is really a part of forces. So you see, even my story started off with looking at forces, because what does forces change? Forces changes acceleration, and you'll be, if you do not have that motivation, you'll be wondering, well, okay, I have these variables all sort of go in circles. Where am I going with this? But now we have a very clear logic is, well, we look at forces, and forces affect acceleration. And once I know acceleration, I can integrate that with respect to time, and I can find v, I do an integration, and I can find the position function, right? I can find the position at every single point in time, and find the velocity at every single point in time. All right, so however, so far, we have looked at motions of one object, right? And now we are going to move on to how 2 or more objects interact with each other. All right, so there are interactions at play, right? So we'll start with 2 or interactions between 2 objects. Between 2 objects. Okay, if you can do interactions between 2 objects, you can do interactions between any objects. It's just added complication. There's no new concepts. There's no new physics going on, right? Think about it. If I want the interaction between 3 objects now, if I understand how 2 objects interact, and now if I have 3 objects, then just analyze the interaction between these two, and these two. So if you have more objects, you can just pair them up. So that's almost that's all we need, right? We just need to know, after we understand how one objects work, then we just need to look at two objects, and we almost finish the story. That everything else is just extra details. It's not new concepts from there, right? So just really just to reassure you, well, by doing that, we'll introduce the last and the famous Newton's third law of action and reactions. We'll talk about that. But just quickly, as to put everything in perspective, to let you know where things are, we really have been able to make predictions, even though we focus a lot of the homework problems, right? You probably immersed yourself in just playing with the Suvat equations, but just don't forget that you actually have learned something new about how to make predictions about the future. Whenever you learn something, you always want to ask, am I better off by learning something, right? So what is better, what made your life better off by learning kinematics? For example, now you're able to answer very practical problems, right? For example, if you're an astronaut, well, no, let's say probably you won't be an astronaut. Let's say since a lot of you are in the pre-med track, maybe you become a doctor, right? So one day, let's say you're gonna, there's a building, there's a tall hospital, and you have a patient living on the 10th floor or something like that, very tall in the building. So maybe it's 30 meters tall, and you're going to work, and you need to deliver some prescriptions, some drugs to your patient. So you walk to the bottom, and now you need to throw it up to the window. Maybe the elevator's broken or whatever. So now you can actually calculate exactly what speed, your initial speed, you need to launch your pack of drugs to be able to reach 30 meters, right? In fact, that's a good question. All I have to do is change some of the objects, like this could be a tennis ball, and it could be one of your textbook problems, or even worse, an exam problem. So see if you can find out what is the velocity you need to launch something that can reach 30 meters of height. Okay, it looks like, do you have enough information? Well, we need 3 pieces of information, right? So I know the displacement. I know, what else do I know? It looks like that's the only thing I know, but that's not true. Other information are already implicit, right? That's actually all the information you know. Can you see from the Suvat what other variables do you know in this situation? Right? Acceleration. Yeah, acceleration is 9.81, right? Meters per second square, pointing in the downwards direction. You can decide which way you call positive. You can call that way positive, whatever. And then you know how to fill in the positive and negative for the displacement, for S, U, V, A, T, etc. But that's only 2 pieces of information. What's the third? You need to launch it to here. So at the velocity over here must be 0, right? That's the maximum height you want to go. It can be larger than 0, I guess, but at a minimum, this has to be 0. And now you have 3 pieces of information, and you can calculate this. And in fact, you can also calculate at what time, if you launch this, how many seconds later your patient can receive the delivery, right? So very practical, very useful. Or sometimes, let's say you have another patient and also living on the 30th floor or 10th floor, let's say. Usually 1 story of a building is roughly 3 meters. 2 meters is the height of a door. That's a good gauge, right? So around 3 meters-ish. So let's say a 10-story building, and you have a patient that one day loses the will to live and wants to jump out of the window. And then they ask you, hey, doc, how long do I have to live? This is one of the most asked questions, right? So now you'll be able to actually answer very precisely. You can calculate exactly, if you jump out of a window, how long you have to live. You don't need to guess and say, oh, maybe a minute or 2. No, you know exactly up to 2 significant figures, depending on which G you use. And yeah, to answer that. And if he or she asks, hey, that sounds rather short amount of time. What if I give myself some initial velocity and I start running, right? I start running and launching myself further. Will I spend now longer time in the air, right? Do I have longer to live? And now you can, for 100% certainty, say that as long as you don't have air resistance, or the air resistance isn't that much, basically you don't have extra time to live. It's the exact time. So might as well save yourself some energy and just drop there from rest. so obviously you won't have this scenario in an exam because it's probably examinations don't appreciate dark humor. But all I have to do is just change this into an apple, and this could be a realistic examination question, right? So these are very useful. You can see that if you add a little bit of imagination, you can actually do a lot of real life problem and real life problem analysis. Things in real life are not necessarily given, oh, things have 3.01 meters per second, and what happens? It's about looking at a situation and analyzing it. Right? So now we're going to move on from one object, because if you look at all this here, I was very curious about the package of medicine. Here, I'm curious about whatever's falling there with an apple or a person or whatever. I'm curious about one object and all the forces that acts on just one object. But now we're going to move on to look at forces that act in pairs. So for example, we have a little bit of them already. If I put a box on a table, right? So obviously the table is in contact with the book. So it's there's a normal force pushing the book. So if I am interested in the book itself, then the book will feel that. So this is basically sort of we have been very taking a very almost self-centric view of just thinking, what do I feel? But now we haven't cared about how about the poor table that is supporting the book. What does it feel, right? The table also feels a force because of the same kind of force from the book. So there's a force, there's a normal force. You can call it pushing or normal force, but normal in the sense that it's perpendicular to the surface of contact. So the normal force there's a normal force on the book by the table, which is usually what we were, or the box or whatever we were caring about. But the thing that is providing that, so far we've just called it the source and just ignored it, right? We just cared about what I feel, right? But now we were going to care about, how about the other poor guy? What's the force on, let me flip that around, right? Flip the subject and the object around. So the force on the normal force on the table by the book. How are they related? Like that. Okay. So I started with two thinking questions on Piazza. So I'm going to repeat that over here in case you haven't seen it, and give it a quick think before you start this next video with these two questions. The first question is, if I have a heavy truck, right, moving and crash into a car. Again, I don't know why things are very violent in physics. tend to be that way. So when the moment they hit, right? So I'm going to move the car all the way to here, right? So the moment of contact right over there. So there's a contact force over here, right? So the truck is in contact with the car is in contact with the truck. So let's draw the free body diagram for this. By the way, there is of course a weight for the book, and there's a weight of the table, the book, etc. I'm just focusing on one particular pair of force where I can look at the opposite of the effect that way, right? So I'm just focusing on one specific force. Yeah, so here that's the same story. There's a normal force from the ground, there's gravity, etc., etc. And but I'm focusing on the contact force over here. So the force on the car by the truck versus the force on the truck by the car. Now, my question to you is, which one's larger? Now, this guy has a larger mass than this. So use big M and little m for that. All right, so that might be a red herring, but which force is larger? Is the truck's force on the car or the car's force on the truck? All right. Question 2 is, we'll learn actually in a couple of lectures, just glancing ahead a little bit, everything with mass attracts everything else with mass. Okay, so the Earth actually pulls on the moon and keeps it in the orbit, and the moon also pulls on the Earth, right? There's a gravity by the moon that is pulling on the Earth. Okay, so the Earth is pulling the moon forward. The moon is also pulling the Earth back towards itself, right? They both sort of attract each other. The moon's pulling. So this is the force on Earth by the moon. This is the force on the moon by the Earth. Okay, which one's larger, right? So the force on the Earth by the moon is what causes the tides and the ocean, high tides and low tides, and the rising and lowering of tides. The force on the moon by the Earth is what's sort of keeping it in orbit and doesn't fly out into outer space, right? Which one is larger, right? Obviously, the sky is much more massive, and does it have a stronger gravity pull on this, or does this have a stronger gravity on pull on that guy? Okay, so think about these two questions, and let's reveal the theory behind it in the next video.